My name's Harvey, and for the final project I made a smoke and fire simulation. The approach that I took for the smoke simulation was to use Eulerian Fluid, which essentially means that the smoke will follow the change in flow at a given point in space. And so I defined my space using a grid approach so that each pixel will correlate to a spot in the grid so that I can define the smoke and its properties and then directly show that to that pixel that it correlates to on the screen. To simulate the actual smoke density and flow, I used a simplified Navier-Stokes equation you see on the right, the top being the velocity equation and the bottom being for the density. And so both of these equations can be solved using the diffusion solver as well as the advection solver. For the diffusion solver, essentially what you want is for the intensity to spread to neighboring cells. And to do this, I use the Gauss-Seidel method, which essentially finds the density where, when diffused backwards in time, leads to your current density. And so doing it this way also gives you more stability than if you were to forward solve. For the advection solver, I also use a backwards solver, meaning that you're going to follow the flow of the velocity backwards to see which cell you end up in, and then take the density of that cell to set the current cell density. And so doing it backwards like this also increases stability, like in the diffusion solver. So for the velocity equation, you're also going to need a projection step. And so what this means is essentially you take your velocity field and you're going to subtract a gradient field from it, and this will give you a mass conserving velocity field, which means that any velocity going into a point on the grid is going to equal the velocity coming out of that point. And so this will ensure nice swirls and nice non-compressible fluid behavior. As I mentioned before, this is a grid-based solver, and so the density and velocity are going to have their own separate grids that you're going to iteratively solve through using the diffusion, advection, and then projection for the velocity. To implement boundaries of your scene, you want there to be no flow exiting the walls. So this means that your v component of the velocity should be 0 for the horizontal walls, and your u component should be 0 for the vertical walls. So in order to transition from smoke to fire, I treated density as heat and then added oxygen and fuel components to the grids, and then through some combustion equation I added oxygen and fuel by some factor to create heat. And based on the heat values, you can color it with a gradient. So higher heat values will be hotter colors of fire, all the way down to the low values will be light smoke. One of my main limitations was very poor scalability for larger simulations. Because of the way I defined the grids to directly correspond to pixels in the scene, increasing the scene size essentially increased the computation time that it took to iterate and solve each grid. And so this made for very poor, choppy looking real-time simulation. One issue I had with the smoke simulation was that it would get really concentrated and really intense really quickly, and so to fix that I multiplied the density of the smoke by some reduced factor over time so that it would slowly dissipate instead of keep building up. And now I'll do the fire demonstration. And so now for the fire simulation, you can see it comes up from this brown wooden block here, which is your fuel. And there's a heat gradient going from white to yellow to orange to red into the light gray and then dark gray smoke. You can see the nice wisps of smoke coming off of the fire. You can also add gusts of wind. You can see it kind of moves with the wind nicely there.